Alright, so this next lesson is usually kind of a fun one. You just apply similarity and just show kind of how useful it is in the real world, and it's really pretty amazing. For instance, if you were at the foot of a cliff and you wanted to measure how tall the cliff was, you know, you could maybe have someone scale the cliff and drop a tape measure down, but there's other ways to get a pretty good idea of how tall that cliff is that are a lot less dangerous. So that's kind of what we're going to look at today, just a couple of problems to use similarity to our advantage. So it says, now that you have a good understanding of how to use ratios and similar figures to solve problems, how can you extend these ideas to situations outside the classroom? You will start by considering a situation in which you need to determine the length of something that would be difficult to physically measure. So, George Washington's nose. On our way to visit Horace Mann University, Casey stopped by Mount Rushmore in South Dakota. The park ranger gave a talk that described the history of the monument and provided some interesting facts. Casey could not believe that the carving of George Washington's face is 60 feet tall from his chin to the top of his head. However, when a tourist asked about the length of George Washington's nose, the ranger was stumped. Casey came to her rescue by measuring and then calculating to get her answer. How did Casey get her answer? Well, there's a lot of different ways that we could do this, but it says figure out the length of George Washington's nose on the monument. Work with your study team to come with the strategy. Show all measurements and calculations on your paper with clear labels so anyone could understand your work. So here's what we're gonna do. I don't know. Shoot, I had a little ruler, but it doesn't have measurements on. So I'm gonna measure this with a ruler on my screen, and I know you can't see that, and that's fine. But I am getting his head is 3/4 of an inch. And I'm getting his nose as 1/4. So if we do this as a ratio, it's going to be 1:3, right? Do we all agree to that? And again, I know you can't really tell that that's what I did, but that's what I measured. I just literally held a ruler up to my monitor and measured from here to here, and then I measured from here to here. It looks like I'm defacing George Washington. Sorry, George. So anyway, at that point, I know I have a ratio of 1:3. Well, think about it. This is his nose. This is his face. And we know that his face is 60 feet tall. The fact that, that we went from 1/4 inches to 1:3 is sort of irrelevant, right? 0.25 over 0.75 is 1/4 compared to 3/4. So if I put an x here, I cross multiply, I get 3x equals 60 divided by 3, x equals 20 feet. And that's pretty good because I looked in the answer and it said that the answer is actually 21 feet. So our little guesstimate of just measuring this and using that scale of similarity worked out pretty well. All right, if we go to 2-101, we do this in class. It almost always works. I think there's been 1 or 2 instances where kids couldn't see, but what you do, it says, legend has it, if you stare into a person's eyes in a special way, you can hypnotize them into squawking like a chicken. Here's how it works. You place a mirror on the floor. Your subject stands 200 centimeters away and stare into the mirror. You measure the eyeballs, right? So we know that this is 200, and we get their height, which, I don't know, let's say is 160. It doesn't really matter. And then we measure this person's height, which let's say is 120, and then we figure out, like, what would that ratio be? 160 over 200. We would have to compare that to 120 over x, right? Well, this would be, I can lob that 0 off, and this would be 4/5. So what would I get to sort of complete this? So I would get 4x equals 600 divided by 4. X would be 150 centimeters. So we would put this person 150 centimeters away. They would both look in the mirror and they would try and see each other's eyeballs. Like I said, it almost always works. It's obviously no fun to do right now because no one's here to do that. I'm going to pause and put the final problem. This sounds like it's going to be a quick video. trickiest one here. So, lessons from abroad. Latoya was trying to take a picture of her family in front of Big Ben Clock Tower in London. Fun fact, last time I went to London with my family, Big Ben was getting worked on and you couldn't see it. Anyways, however, after she snapped the photo, she realized that the top of her father's head exactly blocked the top of the clock tower. That sounds like Latoya's fault. She probably should have looked at that before she took the picture. Maybe next time she should look through the camera lens instead of just snapping it the way she did, but whatever. So while disappointed with the picture, Latoya thought she might be able to estimate the height of the tower using her math knowledge. Since Latoya took the picture while kneeling, the camera was 2 feet above the ground, right? So we have this sort of 2 feet above the ground. The camera was also 12 feet from her 6 foot tall father. So there's 12 feet from her 6 foot tall father, who is standing 930 feet from the base of the tower. I'll put like smiley face on the guy. So, and we want to know how tall is this tower. Well, think about this. From the camera, we get something that looks like this. I got to make that taller. So it's kind of a mess here, right? One of the things that kids often screw up here is this 2 feet thing, because the camera's right here, right? Well, the camera height was already 2 feet, which means her dad was really only 4 feet tall, right? Her dad was really only 4 feet tall, and he was 12 feet away. I hope you see what I'm saying, because the camera was here, so this 2 feet of her dad doesn't really matter. We're going to go over... Uh-oh, that didn't go well. We're going to go over here. I'm going to say there's another 930 feet to the tower, and we got to get this height, right? But we don't know what this height is. So now we can set up a ratio. It's going to be 4 over 12 is going to be the same as x over, it's not 930, it's 942. Right? We're comparing it to the big triangle. But then the problem is, once we cross multiply this and solve this, and we can do this a couple different ways. We can simplify this to 1 over 3 and use that ratio instead. Cross multiply, I'm going to get 3x equals 942. I'll divide by 3, so x equals 314. So x is 314, so you might think the height of the tower is 314 feet, but don't forget about this 2 feet that got lopped off, right? This 2 feet is here for her dad. 2 plus 4 is 6. Well, 2 plus 314 is going to equal 316 feet. So that's how tall it's going to be. I'm going to pause and see if my answer is correct. 314 plus 2 is the 316, so that was what we were hoping to see there. So, perfect. Super quick video. I guess watch it twice if you're stuck on it, because I know it might have went fast. And obviously reach out if you have questions.